yeah, HTL material. Okay, novel HTL material, which is doped with magnesium. So which why we have doped with magnesium, because it will give a more that absorption profile. Here WO3, it's ETL. So now this is the interface to design. So here you can see that this slide, this is the spectrum. Okay, it is, what is the spectrum? The value, it's 1.5 am. Okay, so here this green line means it's ETL, red line means it's HTL. Okay, is doped with electron, doped with holes, or you can say donor, right? You can say acceptor, you can say here acceptor, here donor, like that. Okay, so red line, where we have used, it's CIGS. Okay, so that's why it's coming in red color. So here you can see that that current is going through this line, means from which line? This right side. Here you can see the same thing. Okay, from this side the photon is inserted, and it will go to the ETL first. Here you have written WO3 CIGS, means in place of CIGS if you put the perovskite also, it's also fine. Why perovskite will absorb the photon as it is incident on the WO3? WO3 means ETL, because the ETL is just a layer to transport the electron. Its absorption is very less. So, so as I told you that that there is a continuity equation, A plus R plus T equal to 1. So here, as the absorption of WO3 is very less, so it will go inside, or it will transmit through the layer, and it will hit the CIGs as it is transparent both. So CIGS it will hit. So in CIGS, what will happen, that it will there is a conduction band and valence band for this second generation solar cell also. So it will, as you know the basics, that the holes will be will jump to the conduction band, and rest process will be taken by drift diffusion mechanism, right? This is the basic thing. Now these are the first layer formation, and you may think that this is it, we can just design the solar cell. It's not like that. So I have just named this device. Okay, name this layer. Now if you go to the interface value here, this particular interface provides the details about this particular magnesium, Q plus chromium oxide, and CIGS. There's an interface right in between them. Here also there's an interface. How many interfaces are there? Two. One, two, right? So in these interfaces, what is the defect value? There is always problem of defects. So how we can understand the defect problem, or how can solve it using this simulator, we'll try to understand. All right. So so we have to now, as I told you that you have just designed this and it's not like that. So we will go, you will just, if you click on the CIGS, I have just named it. So if you click on the CIGS, what will come? That CIGS here having a thickness of 0.5 micrometer. Remember that, okay? 0.5 micrometer means it's 500 nanometer. Okay, so CIGS material. Now you can have these inputs. Okay, these are the inputs. Now from where you can obtain these inputs, you just go to the previous publication, or previous literature, or previous experiments from where you are taking. So from their experiment, all the values will be taken from the experiment. Now if you go to the electron affinity, dielectric permittivity, CV, VB, that means conduction band effective density of state, valence band effective density of state, electron thermal velocity, these are always kept. Just remember these both the values we are keeping it same. Okay, because it will not that much affect, it will not affect that much. But here the primary concern which is related to efficiency increment or other factors are electron mobility, hole mobility, like that. So these are taken from the previous experiment. So we can see, or we can say that it's not a only simulation, it is based on the experiments which is done previously, where we are using the property of a particular material. Suppose if you can have an idea about the ball, a football, then means suppose there is a football of radius let's say 20 centimeter, it's a radius, okay, or 15 centimeter, this is the